In question number 1, we're asked to consider the following scenario. 4 children are born and the number of boys is noted, and make a probability distribution, or a PDF. So we start by assigning a random variable. We'll call that X. So how many boys are possible for our 4 children? So we might have, out of our 4 children, 0 boys, 1 boy, 2 boys, 3 boys, or all 4 boys for our 3 children. So these are the number of boys that could be possible in 4 children. So your book suggests that you set up a tree diagram. I'll do that a little bit later. What I suggest you do, since we've already done sections 9.2, 9.3, and 9.4, is look at this as some type of probability that we have calculated already. So how can we have 1 boy or 0 boys in these 4 different scenarios here? Each arrangement or each different type of mixture of boy and girl is different. So we might have boy, 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 girl, but this would be a different scenario than girl, boy, boy, boy. So these would be 2 scenarios where we had 3 boys, and we would count them up as 2 different outcomes. From section 9.4, we did binomial probability, and that is what you see here. You either, for each child you have a certain outcome, or you don't. You have 2 possible outcomes. So if we let a success, thinking of binomial probability, equal to having a boy, then the probability of having a boy is 1/2 for each child. So the probability of not being successful is also equal to 1/2. So that would also mean we would be having girls. So 0 boys means we are having all girls. So if you think about your successes, we're going to have 4 children, and we want none of these to be boys to start with. The probability of having a boy is 1/2, and we want none of those. And the probability of not having a boy is 1/2, and we want 4 non-boys. So if we throw that all into our calculator, we're going to see the probability is 0.0625. So we're going to keep going. The probability of having only 1 boy or having 1 success is 1/2 to the first power, and then also 1/2 to the third power. So making sure these exponents match the number of, in this case, children we're having, but the exponents need to match the number of trials. So if you throw this into your calculator, it is 0.25. And we're going to keep going. 4 children, we want 2 successes, so 1/2 to the second power and 1/2 to the second power. Throw that in your calculator. All right, keep going. 4 children, probability that 3 of those are boys, 1/2 to the third power, 1/2 to the first power, for a probability of 0.25. And then 4 children, all 4 are boys. Probability of boy is 1/2. We want 4 of those. And other children, we want 0. So 0.0625. So we have all of our probabilities to enter into our table. All right, so your book suggests using a tree diagram. You could do that as well. So you would start by branching out. First child is either a boy or a girl. Your next child is either a boy or a girl. Your next child is either a boy or a girl. And your last child is either a boy or a girl. So you would follow the branches and you could count if you wanted how many total outcomes there were. You can list them if you want. If you start with the top branch, you start with boy, and then boy, and then boy and boy. I would kind of mark the branches that you've decided to take. Continuing on this branch, we could have went boy, 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 and then girl. So mark that one off. We've used it. We could have went boy, boy, girl, boy. Or boy, boy, girl, girl. And you would continue to follow these branches until you'd used all of the branches. Writing down each one. So here I have 4 boys, here I have 3 boys, here I have 3 boys, and I have 2 boys. You would see how many total outcomes you have, how many of those followed the description: 0 boy, 1 boy, 2 boys, 3 boys, or 4 boys, and create a probability in that manner. Or you can use binomial probability. In question number 4, it says 2 names are drawn from a hat signifying who should go pick up pizza. 3 of the names are on the swim team and 2 are not. The number of swimmers selected is counted. So we have 5 total people. We have 3 swimmers, which also means we have 2 non-swimmers. We are drawing 2 names from a hat. And it says the number of swimmers selected is counted. So when we make our table or do our probability distribution, our random numbers are the number of swim team members that could be drawn from the hat. So since there are total 3 swim team members, we might get 0 swimmers, 1 swimmer, or 2 swimmers. At most 2, because we're only drawing 2 names from the hat. So what is the probability that we pick a swimmer? So using combinations from section 9.2 and 9.3, we're picking a group of people out of a set. So we can use combinations. First, we want no swimmers. So we have 2 non-swimmers, and we would like 2 of those to be part of our group. And we have a total of 5 people, and we're choosing 2 from that 5. So if we plug this into our calculator, we're going to get 1 over 10, or 0.1. So next, we want 1 swimmer. So from our 3 swimmers, we want 1. From our 2 non-swimmers, we also want 1. For a total of 6 out of 10 as our probability, or 3 out of 5. Now put the decimals there, the fractions are fine too. Next, we want both of our people that are going to get pizza to be swimmers. So we have 3 swimmers. We want to draw both of those as swimmers. And the bottom, total number of outcomes, we have 5 total names, and we're picking 2. So plug that into your calculator. And we're going to get 3 over 10, or 0.3. Your book, like I said in the headline, suggests that you do this as a tree diagram, and you could do it as a tree diagram. So your first choice in picking a name is swimmer or not a swimmer. The probability that you get a swimmer on the first draw is 3 out of 5, and the probability that you get a non-swimmer is 2 out of 5. Then you're going to draw a second name, and that second name will either be a swimmer or a non-swimmer. So if the first name chosen is a swimmer, now you have 2 out of the 4 remaining people that are swimmers. If the first name chosen is a swimmer, now you have 2 out of the 4 remaining people that are not swimmers. If the first name chosen was not a swimmer, then the probability that the next name chosen is a swimmer is now 3 out of the 4 remaining people. And for not a swimmer, 1 out of the 4 remaining people. So here are the possible ways you could move down your branch. You could pick a swimmer and then a swimmer. So 2 swimmers. Multiply that together and you're going to get 0.3. You could have picked a swimmer and a non-swimmer. So this was swimmer, swimmer. You could have done swimmer and non-swimmer. Down here, you could have done non-swimmer and swimmer, which is the same thing as this one, so we'll just add those together. So these are the same set, 1 swimmer, 1 non-swimmer. And then finally, you could have done non-swimmer, non-swimmer, which is 2/5 times 1/4. So there are your probabilities, the 0.3, the 0.6, and the 0.1 for how to draw the names or the number of swimmers coming from your group of 5 people.